Well, welcome back. It's a great pleasure again, this time to introduce Charlie Bennett. I've known him since 1979. It's been, what, 34 years. And of course, our first meeting led to the invention of quantum cryptography. And then we went on working on many other things like teleportation. But so Charlie will tell us about quantum communication resources, one of his pet topics.
Well, I'm very glad to be here. This is my first time in Chennai, and it's a very beautiful place. I've been scared of how hot it was, but I've been in much hotter places that were less beautiful. So I'm going to try to talk about this rather broad topic of how quantum communications theory has led to a proliferation of different kinds of resources. That is, things that you can measure how much there is of it, how much you need of it to do a specific job, and you can use up one resource in order to produce more of something else. Now, this kind of approach was already implicit in classical information theory. In the early work of Shannon, for example, that you can classify all information sources by their entropy, which is how much capacity you need to encode them accurately, and you can classify channels by their capacity. But when we come to quantum information, we get many more kinds of things, especially involving entanglement. So I don't think I have enough fingers and toes to count all the different important kinds of resources that are used in quantum communication and that can be...
You mean more than 1 million?
No, I'm counting in unary.
Oh,
yes.
Oh,
okay.
Really? Why?
All right, well, let's see if I... somewhere, if you count that way, I think that it's about this many. So, thank you, I guess. So, this gives you an idea of some of the different kinds of things. For example, we'll have, in general, some transformation of a quantum state of a system that actually consists of a number of parts that have limited ability to communicate with each other. And often we will allow unlimited local operations in each of the parts. And we want to transform some initial state of this multipartite system to some final state. For example, we might want to get a qubit from here to here, even though we're not allowed to communicate quantumly between these two, but we share some entanglement beforehand, and that is an example of teleportation would be used to do that. The kinds of resources are classical communication, for example, quantum communication, noiseless or noisy quantum communication, or an interaction Hamiltonian. We turn it on, let it run for a while. And we could even consider, well, here I've mentioned previously shared entanglement is a kind of, these are dynamic resources. They go from one side to the other. And this is a static resource, shared entanglement. And another static resource is the opportunity to perform irreversible operations, which generates waste heat. So that's as a sort of a negative resource. Well, it's a resource, what you should say is the resource there is refrigeration. Because if you didn't have it, you could not generate the waste heat. So you can ask these questions in an exact setting. We have some initial state of the multipartite quantum system leading to some final state. What's necessary and sufficient to do that. Or, as is more common in information theory, or as is really more properly called Shannon theory, this part of information theory, in the regularized setting, where we ask what resources are required to convert a large number of copies of this state to a good approximation, asymptotically perfect approximation, to a large number of copies of that state. What? Well, close to the same number. I should put another approximately up there. Yes, that's a good point. I didn't put a parenthesis. That's what I meant. And so we, in any of these transformations, we have the notion of equivalence, or a one-way conversion. I can go from this to that, but not back, or two things which are incomparable. Or more complicated things like catalysis, where a transformation that's impossible by itself can be made to occur with the help of some other resource that is left undisturbed, or approximately undisturbed by the transformation. And an extreme example of catalysis, which I'll talk about a little later, is embezzling. And this is where you start off with nothing, and you have a catalyst system which is very large, and it creates something that you couldn't have made by itself. For example, an entangled quantum state between two parties. And of course, it can't do that perfectly. The embezzling state is changed a little bit, but so little that nobody will notice. So that's sort of the philosophy of embezzlement in the banking world. You steal a little bit of money from everybody and no one notices, and then you buy a vote with that. So here's an example of a kind of transformation of resources. We often speak of a standard EPR pair, a standard maximally entangled pair of qubits. But when we have an experimental apparatus, it often generates something that's less than perfectly entangled. So, for example, the coefficients of this is horizontal and vertical photons. So I've got a red photon that's horizontal, and a blue, the red photon and the blue photon are in this entangled state, which this is supposed to represent equal coefficients. And this is unequal coefficients, very nearly to both horizontal. And you can do a mathematical or a physical operation on this that will gamble with this entanglement. So it will take this state, and sometimes it gives you this ideal state that you wanted, and sometimes it gives you that. So that's a kind of entanglement transformation that's probabilistic. What? Oh, you know yes, you at the end you know which of those things has happened. And so if you do it a lot of times, you can expect a certain yield. So in the looking back at the history of this thing, Schrödinger was amazed to discover that a pure state of a compound system could have impure parts. And he had the correct insight from our current way of thinking that this was revolutionary. But most people didn't think it was very revolutionary until the work of Bell in the 60s. And it's the subsequent work on the theory of quantum communication, for example, Wiesner's superdense coding, it became evident this entanglement is not just a philosophical curiosity, but it's a resource that can be generated and stockpiled and used for various purposes. And I should say always that, well, I shouldn't say to this audience because most of you have studied quantum information in some way, but even if we find it easy to understand or relatively easy to understand, we face the world out there full of people sure they could never understand it. And with, you know, their minds are full of things like dead cats, which make it hard to focus on the essentials. So in a way, we shouldn't emphasize how counterintuitive it is, except as a way of cultivating our own intuition to make them more accurate to the way the universe is. So here's some, but I would say I found this counterintuitive about teleportation. This idea that an orderly whole can contain disorderly parts is certainly a new idea that you need to take on board. And also the idea that you can get something from here to there by sending something from here to here is a little strange. Well, here's an example of one kind of resource transformation that I was just talking about. Entanglement, concentration, and dilution. That is, I showed you the picture. This is another picture of it. I have a large number of weakly entangled quantums, well, I call them pairs of qubits. And what I want to do is to generate a small number of highly entangled ones. And you can do that pretty well. It's a probabilistic transformation, as I indicated with the entanglement gambling. But if you have a large number, you have a high certainty of attaining a yield that is that it conserves the entropy of entanglement very nearly. Then the reverse transformation, suppose we have some perfectly good EPR pairs, and we want to convert them back to these diluted ones. Well, that's not so easy. It doesn't work with perfect fidelity. That's what these little specks in there indicate, that this is not really a product of separate, perfectly weakly entangled pairs. There's a little bit of entanglement among them. So it only becomes exact in the limit of a large number of pairs. And it also requires some other resource, which was kind of neglected at first. But you need some kind of, some amount of one-way classical communication to get this to happen at all. So let's look at see how this works. An example of this is, as I said, this entanglement concentration. You can take an initial state, which is a lot of copies of this weakly entangled system, and Alice can measure how many H's she has, but not in which positions they are. And that follows a binomial distribution. And then that residual state after measuring is a maximally entangled state with about that many equal terms, which can then be converted by local actions into that many perfectly entangled pairs. If you want to dilute it, this is a somewhat inefficient way of doing it. You just take this state locally in the lab, then you make the Schumacher compression, which I'll remind you of later, and use it to teleport. But that's actually a linear amount of EPR pairs. We can do it by a square root amount. So these two things look almost opposite, but they're not quite. In entanglement concentration, what we're trying to do is to take this partly entangled state, many copies of it, into that row really is supposed to be not imply a mixed state, but a pure state, into one of its degenerate eigenspaces, resulting in a maximally entangled state of this smaller amount of entropy. And this state has low fidelity compared to that. You can see they don't overlap very well. But it retains most of the entanglement. So our goal there is not to get a final state that's very near the initial state, but is to get a final state that captures most of the entanglement in the original state. Now, on the other hand, in Schumacher compression, the goal is to get a final state that is very close to the initial state, even though it's not a maximally entangled state. And so in terms of that spectrum of eigenvalues, what we're doing is, instead of picking out a single eigenspace, we're cutting off the tail, which has a great many states with very low weight, and we just forget about those. And the remainder here has very high fidelity to the original state and has about this same amount of entropy. So that's just a hint of the kind of subtleties that creep in when we try to develop a theory of resource transformations. Yes?
Is it a theorem that you deliver unique communication?
Yes.
When I don't have the language, please repeat the question.
Oh, yes. I didn't hear the question because you don't have the mic. The question was, is it a theorem that you need communication? Yes, you need this square root amount of communication, and the reason for that, from the hand-waving point of view, has to do with that's the width of this.
That proves that you need it if you do it this way.
Yes, that's right. Well,
You need communication no matter how you do it.
yes, unless you use them in embezzling state. Well, you know, which is yes, you do need it. The thing is, the reason that you cannot generate if you start with a resource that has a concentrated Schmidt spectrum, you can't get a spread of eigenvalues that's basically the reason. So now I'll go back and start talking about, not about entanglement, but about capacity, channel capacity. And from the starting point of classical information theory, Shannon theory, source entropy and channel capacity, and especially the role of auxiliary resources, which in the classical case doesn't help communication, at least not in the sense of increasing capacity. And then the reverse Shannon theorem, which probably Shannon thought was too silly to have tried to discover. Then we'll go and start talking about quantum channels and really why that theory gets to be so different from the classical theory. So this is probably familiar to many of you, and that is that the foundations of the theory of communication developed by Shannon is to say that every source of information can be expressed as a number of as let's say a binary channel, a certain number of bits, and the number of bits you need to accurately represent the source by means of some encoder is just the entropy of the source. And then you can recover these signals exactly or with arbitrarily high precision, provided you haven't compressed it smaller than its entropy. And the corresponding part of that for channels is the channel coding or error correction theorem, and that says that that every noisy channel has a certain capacity, which is the maximum rate at which you can send bits through it and still get them out with arbitrarily high reliability. And Shannon pretty much posed and solved these problems in the same paper. Of course, this doesn't mention all of the complications of channels with memory and channels with the continuum distribution of signals and energy bounds and so on. But in the discrete case of a discrete alphabet and memoryless channel and a memoryless source, the source entropy is just, and the reason Shannon called it entropy is that it's given by this formula, which had been discovered earlier and used in statistical physics. And the capacity of a channel is just the maximum over the input distributions of the input-output mutual information. So here what I mean here is by H is the entropy function up there. X represents a distribution or a random variable with a number of different values over the alphabet of X. And this N of X means the noisy processing of that is the output signal. And this is the joint input-output signal of a single use of the channel. So these three entropies, the sum of these two minus that one, and maximizing that over the input distribution gives you the capacity of the channel. So these are very simple formulas, and one would hope that the theory of quantum channels could produce comparable simplicity. Now, to take a little detour, but besides characterizing these sources and channels, I suppose I could do it like that, or I could do it like this. Yeah, how about that? Besides characterizing the sources and channels, Shannon undertook to understand the role of some auxiliary resources. I don't think he thought about shared randomness. Well, in fact, he did, come to think of it, between the sender and receiver, and feedback, back communication from the receiver to the sender. And somewhat surprisingly, these do not increase the capacity of a channel. The capacity with feedback, even though it helps very much in our everyday communication, like when Gilles asks me to repeat his question, it doesn't increase the capacity. And Shannon had a nice proof of that. And if we have randomness shared between sender and receiver, that also doesn't increase the capacity. Of course, Shannon also discovered that this shared randomness is very useful for communicating secretly. But one place where the shared randomness does help is enabling channels to simulate one another efficiently. Now, Shannon was an engineer, so he would naturally think of the task of taking an imperfect resource and using it to do a perfect job, such as transmitting data reliably. And the similar example that I gave earlier was take imperfectly entangled photons and get a supply, even a smaller supply, of perfectly entangled pairs of photons. But, I don't know, maybe, I guess I have made much of my career is based on thinking backwards about everything, in reversible computing and things like that. So it's hard for me to think of some question without saying, well, what if you do it backwards? So it occurred to me that there should be the question of what if you have a perfect resource and want to use it to simulate an imperfect one? And I think in the quantum case, it's not such a silly question. There may be some situation where you need partly entangled pairs of particles rather than perfectly entangled ones. But it seems like a kind of silly question in the channel, in the classical channel realm. That is the idea, suppose I have a certain number of uses of a perfect channel and I want to use them to simulate a greater number of uses of an imperfect channel. Well, in fact, actually this theory was developed somewhat under a different name of rate distortion theory. They say if you don't care if the signal is perfect, if it can deviate in a certain way, how much can you save in the transmission cost? But perhaps a more mathematically elegant way of doing this is to say, can I use a perfect channel to simulate an imperfect channel? Well, obviously you can. There's what we call the Homer-Simpson method, where you take the perfect signal that you're going to send through the channel and you apply noise to it before sending it through the channel. And that results in a simulation. Then we also called it the Marge-Simpson method. I should say some of these ideas come from, these terms come from Andreas over there. Where you send the signal through the channel perfectly, but then you spoil it at the receiving end. So it's actually possible to simulate a noisy channel by a noiseless one. But these simulations are not efficient. We'd like to, if the channel has a half capacity, we'd like to take simulate twice as many uses of it of the noisy channel by the smaller number of uses of the noiseless one. So it turns out that this is a job that you can't do unless you have shared randomness. And if you do have shared randomness, you can do it efficiently and asymptotically reversibly. So that says, with the help of shared randomness, the capacity of one channel to simulate another, that is the capacity of channel M to simulate channel N, is equal to the ratio of their ordinary Shannon capacities. Yeah, I think the question is it computationally efficient? That's not usually the question we ask here, but I think it can be made efficient, yes. It's not too different from Huffman code, I think. I may be wrong about that. I think it can be made pretty efficient computationally. So we can use this reverse Shannon way of thinking in order to explain in a somewhat different way from the way Shannon did it, why feedback doesn't improve, nor shared randomness, the capacity of a classical channel. Now, you can say that shared randomness doesn't help because any encoder-decoder pair that is trying to simulate a noiseless channel can be de-randomized. That is, you just choose whichever value of the random variable works best and use that all the time instead of the shared random data. Now, feedback doesn't help. Shannon gave its own proof of why feedback doesn't help, which involved the idea of a. How many people remember this? This is, I think, from his Shannon and Weaver. Suppose I'm trying to encode a book in English for transmission without any feedback, but I'm talking to my audience. Well, let's see. Here's the way that we can show that English is redundant. Let's see. I'll pick Gilles. Okay, there we go. Expert in English language. So I'm thinking of a word. Ask me some 20 questions to find the first letter.
Is it between A and M?
Yes.
Is it between A and F?
Yes.
Is it between A and D?
That's a silly question. Well, anyway, knowing the frequency of words and letters, you would always divide it into sets in which you knew that the probability of the two was almost equal.
As opposed to number of letters, of course.
And if you knew...
But you gave me 20 questions. Why did I have to worry? With 20 questions, of course I can do it, without even having to think.
Well, this is the disadvantage of feedback, I should say. So the point of view, if you had a feedback situation like that, and you knew the person that you were talking to, say you were trying to talk to your wife or something like that, or your husband, then they would already know what questions you were going to ask, so you wouldn't have to ask them, they could just answer them. And that's why feedback doesn't help. But to look at it from the reverse Shannon theorem point of view, if feedback helped a noisy channel, it would also help a noiseless one, which would violate causality because I can use the noiseless one to simulate more uses of the noiseless one to simulate more uses of the noise. Read it. I can't say it as well as I wrote it. So it would seem that there's might be a very nice and simple parallel between quantum communication theory and classical communication theory. Because we have these parallels, we have Schumacher compression is the direct analog of classical data compression. The quantum error correcting codes that we've studied so much is the direct analog of classical error correcting codes. Entanglement seems to be a good analog of shared randomness. And it turns out to be much more complicated. And the question is maybe a somewhat philosophical question. Why is it so complicated and different? In part because entanglement behaves so differently from classical correlation, from shared randomness. In particular, I just said that if you had a probabilistic algorithm, you can always de-randomize it when it's working on deterministic inputs. But you can't de-entangleize an entanglement using algorithm, such as teleportation. So in other words, right there, if you think the teleportation circuit, there isn't any non-entangled state that you can substitute for the shared entanglement and get it to work as well. Another reason, which is really the same reason in different clothing, is the no cloning principle. And because of that, we have a richness of quantum resources, which I'll allude to later. One copy of a quantum state is not the same as knowing what the quantum state is. It's not equivalent to 2 copies or 3 copies or 4 copies. So these distinctions don't exist for classical signals. If I have 1 copy of something, it's equivalent to knowing the whole thing. So let's look at some of these quantum channels and their capacities. Well, first of all, what is a quantum channel? A unitary evolution of a quantum system is reversible and it preserves distinguishability. But a channel in general can be lossy or noisy. A specific example of that is a classical channel which spoils superpositions. Or an erasure channel which destroys signals completely. I'll speak of these more in a short time. And so the mathematics of this is that any physically possible evolution of an open quantum system can be modeled as a unitary interaction with an environment which is initially in a standard state. Well, here are some of these channels, some of the simplest ones. The noiseless channel, you send these qubits through and they all get there. The erasure channel, which has a certain probability of losing them. So at the receiving end, you get the qubit, or else you get a signal that tells you the qubit didn't get there. The depolarizing channel, where the qubit is replaced by a random qubit. You can't tell. This is the analog of the binary symmetric channel, where the data looks perfectly good, except that some of it doesn't match the input. And then this is a specifically quantum thing, where it will spoil superposition sometimes, as if one of these qubits got measured and then resent by an eavesdropper along the way. So you can develop the theory of the, I like it's better this way, of the classical and quantum capacities, quite parallel to the way they're defined for a classical channel. And so the idea here is the quantum capacity of this noisy channel is the maximum rate at which you can send signals through using a quantum encoder and decoder, which are, again, these completely positive maps that give you an asymptotically perfect fidelity between input and output. The classical capacity would be the same expression. So here we're talking about the classical capacity of a quantum channel. May I borrow one of those bottles of water? I think I need that. Is one of those for me? I guess I'll take one and see if anybody complains. I don't think I'm going to use all this, but but in the terms of a quantum channel, we can't just talk about input letters and output letters. We have to say that the input states are chosen from an orthogonal set, and we want that the output coming out reproduces that with high fidelity. So essentially we're saying it's like the quantum capacity, except we only average over an orthogonal set of inputs. So this looks like a very parallel theory. But the quantum channels end up having a lot more different kinds of capacity. One of these is the, which is kind of obviously important, is the private capacity, the capacity for sending classical bits privately when Eve holds the environment. And it's clear that that these three are monotonically related. If I can send quantum information intact because of no cloning, I can therefore send private information. And if I can do that, then I can certainly send information which I don't care whether it's private. But then there are these other funny capacities, like the quantum channel capacity assisted by backward classical communication, or even two-way classical communication, or the entanglement assisted capacity, where sender and receiver share entanglement, and we want to see how much classical communication can go through the channel with that. And unlike the classical Shannon theory case, these assisted capacities are generally greater than the unassisted ones, and the formulas for them are, in most cases, pretty complicated, but in a few cases, much simpler, or equally simple to the classical Shannon theory. Here's an example. The quantum erasure channel is characterized by the erasure probability, and it has, of these 5 different capacities, the ordinary capacity, the classical capacity, which is just like a classical erasure channel, goes steadily from 1 bit per bit, or 1 bit per qubit, down to 0, as the erasure probability goes from 0 to 1. This Q2 capacity does the same thing. The private capacity and the quantum capacity both go down more sharply, so that they are 1 when there's no erasures, and then when the erasure probability is 1/2, they go down to 0. The entanglement assisted capacity is parallel to that, but goes all the way up to 2. So this is really the simplest case, and is not too hard to understand why that happens. The reason that a 50% erasure channel has no quantum capacity is because it can be viewed as one output of a symmetric splitter. And if we had an encoder that could recover a quantum state that was sent through a symmetric splitter, we could take the other output of the splitter and make another copy of the state. So it would be a violation of no cloning. And that's the reason that that capacity has to go to 0 when the erasure probability is 1/2. If the erasure probability is less than 1/2, you can't view that as one output of a symmetric splitter. And in fact, as simple as it is, the erasure probability, erasure channels with erasure probability less than 1/2 are not well understood what their capacities are and the relations of them. Okay, so if I have additional classical communication or shared entanglement, I can boost the quantum capacity of this 50% erasure channel. If forward classical communication doesn't help, but a two-way classical communication does help, or even backward classical communication. The idea is I use the erasure channel to send halves of entangled pairs, and then I wait for the receiver to report back which ones arrived, and then I use these and forward classical communication to teleport the quantum input to Bob. With shared entanglement, then, I can use the forward classical capacity to send Bob the classical bits that I need for teleportation, and then I already have the entanglement. And then if I have back communication alone, I combine those two. So this shows how to boost why these auxiliary resources help in this case. Now, I've got a whole bunch of stuff which may be very elementary. How many people here are familiar with density matrices and what they mean? Everybody. Okay, I think I'll go through it very fast. So if anybody has any questions about this, just ask me. So I've been speaking about pure states, but now let's speak of mixed states. A density matrix. See, I'm going very fast. A density matrix can represent an ensemble of several pure states with different probabilities, or a situation in which a system is part of a larger system, which is an entangled pure state. And pure states can revolve to mixed states. It's mathematically represented by a positive semi-definite matrix unit trace. And this is how you figure it out from an ensemble or from an entangled state. Different ensembles can have the same density matrix. So what common feature does the density matrix represent? It represents all and only the information that can be learned by sampling the ensemble or observing the A part of the bipartite system. And ensembles with the same density matrix are indistinguishable, and pure states with the same A part are indistinguishable by observing the A part. And then there's this nice theorem that was discovered by many people, including Schrödinger and many others, in one form or another. If Alice and Bob share a system in this entangled state, then for any ensemble that's compatible with what Alice has, there's a measurement Bob can do on his system alone that generates that ensemble and tells him which outcome Alice would get if she made that measurement. So that's what Schrödinger called steering. Okay, so that's, well, I've already talked about von Neumann. Okay, now we're done with that. Okay. What? I think Schrödinger used the word steering, yes. I mean, at one point he switched to speaking English. Yeah. Mathematically, we think of this as a noisy processing of a quantum signal, but we can also think of it as a unitary interaction with an environment initially in the zero state. So it has two outputs, the output to the channel receiver and the output to Bob, and the output to the environment, or Eve. And drawing it as a sort of flow chart, you can have different size inputs and outputs, but we can all imagine that coming from a a unitary transformation that has the same number of inputs and outputs, but these are dummy inputs that get zeros, and this is a dummy output that's thrown away. So this philosophy is called the Church of the Larger Hilbert Space by John Smolin. And the idea is that it helps, at least for some kinds of quantum problems, to think that when anyone says a mixed state, they're always speaking of the pure state of a larger system. And that if we speak of a noisy processing, we're always speaking of interaction with a deterministic unitary interaction with a larger system. So that says a noisy channel can be viewed as a unitary interaction with an environment, and a processing of a noisy input can always be thought of as a processing of an input that's entangled with a reference system that doesn't get processed at all. So we have this looks a lot simpler than this, but in a way this is more simple than that, because here there's nothing but pure states. We say that when we send a mixed state into an encoder and get another mixed state out, what we really mean is that the mixed state is part of a pure entangled state, and the processing that we're subjecting it to is an interaction with an environment initially in a pure state. And what comes out is three things. This state is unaffected because nothing happened to it. This one is a noisily processed version of that, and this is a different noisily processed version of that. And these three systems comprise together a pure state because we haven't done anything non-unitary to them. And this can be described as the identity tensor product, the noisy channel acting on the initial state. And this has the same entropy as that. So that makes it a little easier to think about, even though it's more complicated to draw. So as I said, there are all these many capacities, and these assisted capacities can be greater. And the goal really of the quantum Shannon theory is to find nice formulas for all these capacities, like the ones that we have for the ordinary classical capacity. Well, this is a big mess. And this is, I think this is, maybe the latest information isn't on here. So here we have the thing that we're talking about, the entangled input to the channel, which is a purification of this oops, let's see. Yeah, the input to the channel is a purification of this Q system, I guess, that goes in there. It interacts with the channel, and we get these three things out. We get the rho that it originally had, the noisy output, and the eaves output. And the classical capacity is equal to this. We have to do this. We can't just use the Holovo information. We need this regularization. The private capacity is another nasty formula. The coherent information has to be regularized to get the quantum capacity. This is by the LSD theorem for Lloyd, Shor, and Devitak. And finally, the one nice one is the quantum mutual information. There's no regularization, no limit in the large n to infinity. The entanglement assisted capacity is just the maximum over inputs of the entropy of the input plus the entropy of the output minus the entropy of the environment, which is the, oops, what did I keep doing that? Okay. So we have a mostly complicated situation, which I think has gotten a little more complicated since I wrote this slide, because we have this non-additivity results. There are no good expressions for some of these capacities. And then even the only one that has a good expression is this entanglement assisted capacity. And then we have some really bizarre phenomena, such as if we have two channels that each have no quantum capacity at all, the combination of them can have a positive capacity. This is a Smith and Yard from 2008, superactivation of quantum capacity. So I'll say a little bit about that later. So the I guess I began thinking about this when I heard a talk by Aram Harrow in 2001, at which it was sort of provocatively changed, will free entanglement change the world? And I began thinking about all the people who thought that free something or other would make the world a much better place. Here's Charles Fourier, unrelated to the, or at least not the same person as the Fourier transform person. He was a social thinker, and he was among many of these utopian socialists who thought that free goods and services would make everything better. And the same guy, along with Emma Goldman and lately taken up by the, well, it's not that recently, actually. It's quite a while ago. The hippies in Haight-Ashbury thought that free love would make everything better. And then, of course, Lloyd Short, no, wait, that's different people, would make everything better. And then this is an idea that's kind of current right now. That is that the internet and free communication, freedom of information will make everything better. Well, I don't know, these things didn't uniformly work, but maybe free entanglement will change the world. But at least it simplifies the theory of quantum channels. So here's free classical communication. We get the idea we're sending stuff, we're giving Alice inputs and we're getting outputs from Bob. We're allowed to use the noisy channel, but we don't want to use it any more than we have to. We have unlimited classical communication back and forth. Unfortunately, there's no good formula for that capacity. But if we give free unlimited entanglement, then there is a good formula for it. It makes the capacity larger, and it makes it easy to calculate. And here is that formula that I gave. Again, it says we have an entangled purification of the input. We send it through the channel, and we get this output, which is, in general, still entangled in some way with the reference system. And the entropy of that combination, although I didn't write it here, is equal to the entropy of the environment. So the entanglement-assisted capacity is equal to the maximum over channel inputs of their joint entropy, of the entropy of the input plus the entropy of the output minus their joint entropy. But that's a little funny to say because the input and output don't exist at the same time. The input is destroyed when you go into the channel. So you have to take not the input and the output together, you take the input and the purification of the input, the output and the purification of the input. Or another way of putting it, that is the entropy of the input plus the entropy of the output minus the entropy of the environment, which is the coherent information. So in retrospect, you might have said that what Shannon discovered was the formula for the entanglement-assisted capacity of a classical channel. A very simple formula. That was a kind of a joke, because for purely classical channels, entanglement doesn't help. It doesn't increase the capacity. Their entanglement-assisted capacity is the same as their ordinary Shannon capacity for somebody who doesn't think in the church of the larger Hilbert space. But Shannon also considered another less realistic and much less famous capacity called the zero-error capacity. And it is related really to graph theoretic as opposed to entropic properties of the input-output mapping. It has nothing to do with the probability of getting a certain output when you put a certain input in. You care only about whether the probability is zero or non-zero. And we have channels like this. Suppose we have 3 inputs letters and 3 output letters. This is a classical channel. And the question is how much, at what rate can you send information through this channel with a zero error, zero probability of error? Well, I think it's kind of clear that you can't do anything better than to send a 0 in sometimes and a 2 in the rest of the time. In fact, each of these half the time. Because the 0 can get converted to either of those, and the 2 just stays at 2. So anything else that you can do will only give you some chance of an error. So this is a channel that may have, depending on these probabilities, could have a capacity almost equal to a trit, but it actually only has a 0 error capacity of a bit. Now, entanglement can actually increase the capacity of a noisy classical channel, a noisy classical channel, 0 error capacity. And the idea is we use we have this entangled state, we do something to it here that generates something here, and then we send it through that noisy channel like the one I showed. And with this extra help, we can get a higher 0 error classical capacity. And I like this partly because this is a word that I learned from Wikipedia, and I think it's a very useful word. Disambiguate. I guess it existed before, but it's become much more frequently since Wikipedia. He was just a curious guy. I mean, he spent the later part of his life thinking about stuff that you would consider even less interesting. Okay, well, going back, following Gilles' comments, that why would Shannon care about such an unrealistic thing as 0 error capacity? We'll go back to the ordinary capacity. And we'll say, well, let's see, how about a quantum reverse Shannon theorem? Now, actually, when Andreas and I and the other co-authors on this long, did we start working on this before the year 2000 of this quantum reverse Shannon theorem? I keep thinking of it as our bi-millennial paper that still hasn't been published yet. Anyway, the quantum reverse Shannon theorem was the inspiration of the classical one, I think. We thought, gee, we've got teleportation and dense coding, and we can use, if we have enough free entanglement, we can convert back and forth between those. It's hard to remember, it was so long ago. Anyway, so in the back of our heads for a long time was this idea of a quantum reverse Shannon theorem. That is to say, all these nasty multiple quantum channels capacities can be collapsed into one if we have free entanglement. So the idea would be any quantum channel ought to be able to be simulated by shared entanglement and an amount of classical communication equal or asymptotically equal to the channel's entanglement-assisted capacity. So therefore, in a world full of entanglement, all quantum channels are qualitatively equivalent, and they quantitatively can be characterized by a single parameter. So that's a massive simplification. Unfortunately, it isn't quite exactly true. And that is because when we say simulate a channel, we would like to simulate it not necessarily on inputs that are promised to be many copies of the same distribution, but on an arbitrary input, maybe even entangled amongst the different inputs. So we should say the kind of source we use the channel with is this tensor power source, the simple analog of the classical independent, identically distributed source, which is just a lot of copies of the same mixed state. Then we could have a tensor product where there's no entanglement, but each one of these might follow a different distribution, all living in the same Hilbert space. And the most general thing we could give it is to an entangled purification of an arbitrary entangled state that lives in this large Hilbert space. And that's the worst an adversary could send in order to try to detect the difference between the real channel and our simulated channel. So the idea is we would say, if we've got this entanglement-assisted coding, we've got an encoder, we have some classical communication, no more than the entanglement-assisted capacity amount of it. If we have unlimited classical communication, we can just teleport this from here to there and there's no problem. but we want to throttle down this amount of classical communication to the bare minimum. We have entanglement, and we demand that whatever this state is that comes in here, this arbitrary state that our adversary is testing us whether we're simulating a channel or doing a channel, that it should equal, that the output should have high fidelity to what it would have been if this had been a channel rather than a simulation. And it turns out that we get some interesting complications there. And the complications are, or the complication is, that depending, if this is a superposition of many terms, the different terms in the superposition might use different amounts of entanglement. And then the environment figures out which term went through, and it's not a faithful simulation anymore. So what we need to use is an embezzling state, or one of the ways of dealing with it is an embezzling state. And so the idea there is that we have a simulation that uses entangled pairs, but it uses a superposition of different amounts of them, but we can borrow them from the embezzling state, and the embezzling state is almost the same after we've done this borrowing, right? Because embezzling is actually stealing. And now there's another way of doing it. If we don't like embezzling states, we can have standard entangled pairs, and then we can use backward communication as that's not a very helpful resource for forward communication, but it is a resource that can be used to obliviously destroy entanglement that you don't want, and therefore make all of the terms in the simulation use the same amount of entanglement. Now, this was supposed to be a tutorial, which was supposed to be elementary, but I'm kind of reveling in the complication of this. And I'll show you how complicated it is, which is part of the reason we haven't really finished writing this up yet. Well, we haven't finished dealing with the referees yet. Well, here's the embezzling state. And the idea is it's a superposition of terms with very unequal weights, a very large number of terms. Like with this harmonic series, we weight each term by the square root of the number. So it's the first term gets a weight of 1, the second the weight of square root of a half, square root of a third, and so on. Of course, that series diverges, so you have to cut it off at somewhere. But when we have a state like that with very high dimension, this was shown by Van Dam and Hayden quite a while ago, you can generate an arbitrary quantum state of a lower dimension from it without communication and leave the embezzling state almost unchanged. So that's just what we need for this, and here's how we use it. We've got a channel. This is the channel simulation. Here's our entangled input, and we have to transform to the Schur basis, and now we have some need for entanglement, and we get the amount of entanglement we need out of an embezzling state, and we've got this leftover embezzling state, and then we do some sort of complicated teleportation here, and finally it all comes out right here, and the embezzling state looks almost the same. So if you think that's complicated, this is even worse. This is with backward communication, and that involves taking this apart into several parts, one of which has to come down to the receiver and then go back again to help finish a job that needs to be done up here. I love this diagram anyway, but I shouldn't bother you with it anymore. So anyway, what are some more things we can do with resources? And it still has to do with the reverse Shannon theorem. And this was an idea that was, let's see, maybe Andreas can give me the history of these papers here. This is Roberto Rodriguez who drew this picture. We were trying to get the idea that it's a little hard to express. We have Alice, Eve, or Alice, Bob in the reference system, and they share an entangled state. So here's Alice, and here's Bob, and here's the reference system. And he's sitting there with his arms folded like that because he doesn't do anything. He just has a subsystem of this tripartite system. So by the church of the larger Hilbert space, you can think of any mixed state that Alice and Bob have as something of this sort. In fact, you should think of it that way. Now, the job of what they called state merging, which Horodetsky was that anyway? One of them, and that's Oppenheim, and that's you, right? Okay, well, anyway, you can think of that as saying, well, Alice would like to give her part of the system to Bob, so she doesn't have it anymore, Bob has it. And so when they were explaining this to Roberta, she said, oh, well, what you need is to draw a little doll that looks like Alice. That's her subsystem. And she gives it to Bob, and so now Bob has his part and her part. And that's exactly the idea that we needed. And they showed that asymptotically, in the limit of a large number of copies, that Alice can transfer her share to Bob using that amount of classical communication and that amount of E-bits. Now, this quantity can be negative. This is the conditional information of Alice conditioned on Bob. And so in that case, when it's negative, the transfer can be accomplished in which you generate entanglement instead of consuming it. And so they were really excited about this and wrote about negative quantum mutual information, quantum conditional information, and they tried to explain it to journalists. And one of the journalists in Bristol came out with this headline. So we can think of this state merging as, we can think of it as in terms of various resources. We can say, can we do it with classical bits of communication and E-bits? Yes, we can. The advantage of that is that those resources are strictly incomparable. You can't make classical bits from E-bits nor the reverse. The disadvantage is that it's not reversible. When you say classical communication, you're implying that there's an environment, so it's not really a totally closed system. So you can express it alternatively in terms of another pair of resources, a certain amount of Q-bits and a certain amount of E-bits. And of course, those resources are partly comparable, but the strong advantage of that is the protocol can be made reversible. So we have a protocol that involves some communication of quantum information and some production of E-bits. That is, has a negative cost of E-bits, gives a positive amount of E-bits. And that's what became the scientist knows less than nothing. What's that? Oh yeah, a co-bit is it was a coherent bit, and it's defined as a combination of a Q-bit and an E-bit. That was an idea of Harrow's. So here we have the opposite of state merging is state splitting, and we start over here where Bob has a system and it has two parts, but he has both of them, and then at the end he wants to give this part to Alice. And because this is reversible, the state splitting can Bob can do that job by sending this many qubits from Bob to Alice and by consuming this amount of entanglement. So this turns out to be really just in other words, for the quantum reverse Shannon theorem. We want to say, I want to send a subsystem from Alice to Bob while maintaining its entanglement with what I already have and with the reference system. So we decided that we were going to enact this thing, and I've got some pictures from, this is about 2006 in Paris. So here we are. This is Bob, and this is the reference system, getting ready to do nothing. And we didn't have little dolls. We needed a little female doll, a little male doll. We had to substitute it's hard to see here. This is a wooden mortar and pestle combination. So this is the female part, that's the male part. So initially, both parts of the system are held by Bob, and now he's going to split it. And Andreas holds the purification. He doesn't do anything. Now, we didn't get a female volunteer for this act, so I kind of put on a skirt here. And you can see that Aram is giving me the mortar. But in addition to giving me the mortar, which represents the quantum communication, we both have to consume some entanglement, which is in the paper cups. And in the end, this tripartite system, what used to be held entirely by Aram, is now shared between him and me, and Andreas has the purification of it. Now, this is reversible, and so if you went backwards, you would get state merging, which is, and I'll go backwards right now. We start off with a couple of empty cups, and I'm holding the Alice part of the system, but I want to give it to Aram, and he's holding the other part. And so then we regurgitate some entanglement into the cups. And finally, the cups have extra entanglement in it, which Andreas would call the scientist knowing less than nothing. And Aram has the whole quantum state, and Andreas has the purification of it. Okay, so how am I doing on time anyway? Half hour. Okay, that's good. So, and I'm going to talk about something completely different. So this is many people, when they first start thinking about quantum information, they ask questions like this, and they expect some kind of answer. So how much information is there in a single photon, or in a single qubit, a single photon's polarization? Well, one answer is there's infinitely much information because the polarization requires two real or one complex variable to describe it. And then you might say, oh no, that's an underestimate. It's not infinitely much, it's way more than that, because if you have n entangled particles, you have 2 to the n complex numbers to describe it. Or you could say it's only 1 bit because that's all you can get out of it by measuring it. Or you can say 2 bits because if I have entanglement, I can use 2 bits to accurately teleport the state. Wait. Okay, so the question here then is that what are the different levels of what did I call it? Different degrees of knowledge of a quantum state. The most perfect degree is to have a description of the quantum state, therefore I can prepare as many copies of it as I want. Or I could have a specimen of the quantum state. And this is a big difference between classical and quantum information. A single specimen of the state is different from knowing what the state is. And let's call, I think this was a term that I introduced that was never, I don't think was ever even published. It was just it was a kind of a bad idea I'm trying to recycle now. A mystification of a quantum state is something that enables one to predict the result of a measurement on the state more accurately than if you didn't have any information about the state at all. So an example of a mystification would be the null mystification, which is a complete classical description, or 2 specimens of the state, or 1 specimen of the state, or 1 specimen of the state that is antipodal to the original state, the state of opposite polarization direction, on the block sphere, or a black box containing a single specimen of the state and a place for a classical input port for a description of a measurement to be performed, and an output port. And so that box can be used to simulate a measurement on the state, but you can't get the state out because the box is impenetrable, or it's lined with explosives or something. So the classical knowledge of a state allows you to prepare a specimen of the state, or a specimen of the state of opposite polarization in the block sphere. But those two states are not interconvertible. And if given a single specimen of a state like this, I cannot prepare this state, or even given any finite number of them, I cannot prepare a copy of that. And in the famous paper, Shannon and Popescu showed that a pair of anti-parallel spins convey more classical information about the spin direction than a pair of parallel spins. So this is just one of these really wonderful quantum things that you can't even explain what it is classically. So how does a specimen of the antipodal state enable you to simulate a measurement on the original state? I think I said that before. Didn't I say that? Yes. Given a single... Yes. Classical? No, okay. This is true. The first question was, does a specimen of the antipodal state enable you to simulate a measurement on the original state? The answer is yes. And how does it do that? Well, what we have to do is to perform the antipodal measurement. So if what we're saying is, how would this spin behave if we send it through a Stern-Gerlach apparatus? Well, now I can explain how this antipodal state would behave by just making the upside-down Stern-Gerlach apparatus. And because any classical measuring apparatus, I can make the geometric inversion of it, even though I can't make the geometric inversion of a quantum state, I can use, or to put it in symbolically, a measuring apparatus can always be converted to the antipodal measuring apparatus, but the states cannot be converted to the antipodal states. So this gives this hierarchy of incomparable mystifications of the quantum state. Infinitely many copies or classical knowledge is up at the top, 2 specimens, 1 specimen, being able to simulate a measurement on any 2 measurements on psi, 1 measurement, being able to simulate 1 measurement on psi, and then having a single specimen of psi is equivalent to being able to simulate a joint measurement on psi and some arbitrary other state of which one is given a single specimen. So why is that true? Does anybody know why that's true? That I have a state psi inside a box that I can't get it out, and instead of just an input port to say what measurement I'm going to perform and an output port to give the result, I have 2 input ports, one to tell me what measurement to make, and the other to put in another quantum state that never comes out, and I get the measurement result out. How can that allow me to do anything that I could do with a single specimen of that state? Anybody got some ideas? Well, it's pretty late, and I've been talking for a long time. The answer is, what is my favorite quantum protocol? And also Gilles. All right, we do it with teleportation. So if I have the opportunity to make a measurement on the entrapped state in here and an arbitrary other state, I just do a Bell measurement and I teleport it out of its prison, and then I can do whatever I would want with it. So that's an example of things that you can do with mystifications. Now, I think another paradoxical thing that we noticed was that the job of remote state preparation is to go from a classical description of a state to a single specimen of the state. Now, asymptotically, the cost of that is 1 e-bit and 1 bit per qubit remotely prepared. In other words, half the classical communication cost of teleportation. In a way, that's not surprising because the sender starts with a more powerful resource, knows the state, rather than just having a specimen of it. But if we demand that the remote state preparation be exact and that it doesn't leak extra information besides producing a single copy, then it turns out that the single specimen requires 2 bits to prepare, equal to the cost of teleportation. So I really was fascinated with that result because it says that more words are required in order to convey less information. And this is a very common thing in politics, because when a politician wants to say almost nothing, it turns out to take a lot of words. So here are some other questions that have to do with resource transformations. And this is some non-local storage of classical information in quantum states. Now, this is something that fascinated Wiesner back in around 1970 or late 60s. He said he knew about these Bell states, and he knew that they are globally, and we would say nowadays, they're orthogonal. There are four of these. But if you have them, you can't seemingly distinguish them by local measurements. And so the question is this imperfect local distinguishability a feature only of entangled states, or can product states exhibit it? And are there states that are globally distinguishable, even though, that is orthogonal, even though local efforts to find out what they are reveal arbitrarily little information about them? So now, much of this is understood nowadays, but some early examples of unentangled states that are less distinguishable locally than globally are these three 120-degree angle polarization states, in which we have 2 copies. Alice has the same as Bob, but we don't know which of those we have. And these are the states that inspired teleportation, because we were trying to figure out, well, first Paris and Wooters wrote, they made a valiant effort to find out why Alice and Bob couldn't find out these 3 states as reliably by having them in their separate laboratories as by having them together. And the answer turned out to be teleportation. And this is an old quantum protocol, which was an interpretation of a BB84 type of cryptography as a time-ordered presentation of 2 messages, the first of which must be read before the second one is sent. And this can be viewed as 4 orthogonal states, but it can't be distinguished if communication from Bob to Alice is prohibited. So sharpening up some of these ideas, we got this of, I should say, this is some, I don't even remember all of the collaborators. This is DiVincenzo and Terhal and Smolin and some other people. We came up with these pentagonal pyramid states. You have 2 trits, and the states are, the Alice part of the state is goes in this, gets 1, 2, 3, 4, 5, these 5 directions, which are such that those 2 are orthogonal and these 2 are at an acute angle. And then the Bob part, it goes around by 1, 2, 3, 4, 5, the way you would tighten the lug nuts on a car. So these are 5 orthogonal states that cannot be locally distinguished, and that means that to prepare them from locally orthogonal states generates waste heat, and to go backwards cannot be done locally, even though globally it can be done. So let's see, I'll skip a few of these things here. We're getting close to the end, I think. So here's another thing that I think probably needs some further work, though I haven't thought about it lately. Other people probably have. All non-local unitary interactions are qualitatively equivalent, because they can all produce entanglement, and they can produce for bidirectional classical communication. So this is the story that I always tell about Alice and Bob who are in love, but their parents prohibit them from meeting in person, and they can they can't even exchange email, but they can allow one atom of Alice to interact with one atom of Bob through a hole in the wall that they discovered that their parents don't know about. So it's like the quantum Pyramus and Thisbe story. It turns out if you have an atom of Bob that can interact with an atom of Alice, they can generate entanglement, and they can use it to do classical communication. And with a lot of effort, they can teleport the state of one over to the others, and they can do whatever they want together, and then teleport back before morning. Anyway, so this says that all non-local unitary interactions are qualitatively equivalent. But is there a single measure of an interaction's strength, or are some interactions better for some jobs, like generating entanglement, than for other jobs, like communicating? Now, non-unitary interactions are not qualitatively equivalent evenly. Some can generate entanglement but not communicate. Some can communicate but only classically. And then there are these ones that can't do either but are still non-trivial. Oh yeah, here's the Pyramus and Thisbe story. A while ago, these authors found that the gate's capacity for doing these jobs are equal, but not for larger than 2-bit states. So here's an example of a kind of interaction, a gate that has very unsymmetric abilities to communicate in the two directions. So the forward communication capacity from Alice to Bob is much stronger than the reversed capacity. All right, finally I'm going to close with the phenomenon of superactivation, and that's where we take some worthless resources and we distill out of them something valuable. And the most famous example of this is the superactivation of quantum capacity that was the subject of this article by Smith and Yard. So what we have is we have two different noisy channels, N1 and N2. These are quantum channels. And no matter what encoder and decoder we use, we can't get quantum information faithfully at any rate through N1, nor through N2. There are channels that have no quantum capacity. And yet if we have an encoder which uses both channels in parallel, so the encoder takes a lot of inputs, generates inputs to the channel, and is allowed to use both kinds of channels, and then the decoder takes that, we can get information through faithfully. So that is an entirely strange property, and in fact it means that the set of channels that have positive quantum capacity is not even convex, because you can take a mixture of two channels that have no capacity and get a positive capacity by going between them. Or in other words, it says that there are two different kinds of noise, at least two different kinds of noise in a quantum channel that are synergistic. That is, if I have one kind of noise, it doesn't spoil the signal so badly that it can't be repaired with the help of the other kind of noise. So the two kinds of noise are, well, one of the channels that they use there is the one that we know already, the 50% erasure channel. So half the time it sends through the input unharmed, and the other half it sends an erasure signal. And the other kind of channel is something that I haven't had time to talk about much, but is a positive partial transpose channel. That is a channel that is so noisy that if you try to distribute an entangled state through it, it spoils the entanglement by generating a state that has positive partial transpose. Well, let's say you can still get entanglement, but you don't get any distillable entanglement. And so this is a sort of more complicated channel, but they're not very complicated. These were discovered mostly by the Horodetzkys. And what Smith and Yard showed was that if I have any noisy channel and I combine it with a 50% eraser channel, the quantum capacity of this combination is at least as big as half the private capacity of the noisy channel alone. And what was known before that was that some of these positive partial transpose channels had a non-zero private capacity. So they were not good for sharing pure entanglement, but they were good for distributing cryptographic key. And with this theorem, that means that the help of a 50% erasure channel, which you might say is lossy but not noisy, compensates for the noisiness of this channel, which is so noisy that it spoils quantum correlations, and the two together can be used to distribute to distribute quantum states with perfect accuracy. Okay, so at the end of this, this is just about the right time to end. I think the theory of quantum communication resources, of which I've just scratched the surface and just talked about a few of my favorite topics, is multifaceted, and there are many things that we still don't understand, and many things that we do understand enough to be thrilled by them. And if you want to be thrilled some more, come and listen to Andreas in the afternoon.
Oh, thank you, Charlie. Will we hear from Andreas about things that are poorly understood or well understood? Will we hear about things that are poorly understood or well understood, or both?
Well, after I've been introduced as the man who does nothing and knows less than nothing, I don't think you can expect much.
All right, any questions for Charlie? We have
good reply.
We have 10 minutes before lunch.
First of all, I want to thank you for such a nice talk. And my question is simple. You define many channel capacity. Like in classical communication, like internet, people say that many Mbps speed, that many, you can have that many capacity in classical channel. So is there some number in this case as well, like when you define different capacity, like quantum capacity, experimental number, like that many bits or states, or basically I want to ask, like, what are the experimental effort in this case?
Most of this on quantum communication has been theoretical. Oh, the question, I guess we heard that because of the microphone. Most of these calculations that I've talked have been theoretical, but in efforts to
realizing
say quantum key distribution over long distances, or to communicate within a quantum computer, people are very eager to measure the fidelity with which a quantum signal is transmitted from one place to another.
Mm-hmm.
So they have not so much capacity questions that they've strived to answer, but just to characterize a channel, to find out the input-output mapping of a particular channel that they have in their laboratory or in their...
they use different distance measure, like fidelity.
And I should say this whole Shannon theory is, in a certain sense, an idealization, because
it's an asymptotic limit when n goes to...
It's asymptotic and assumes perfect encoder and decoder. And of course, when people are trying to build quantum computers, they have to do fault-tolerant correction of all of their encoders and decoders involve errors in the... So in that sense, it's an idealized part of the theory to speak of capacities.
Okay, so basically, like not many experiment in, especially in capacity case exist. Or
I should say, though, that people are inspired by the example of classical information theory, classical Shannon theory, where the original codes that were discovered by Shannon were not practical. They involved very large alphabets. And over the years, the performance of actual encoders and decoders has come quite close to the theoretical limits. And it probably, you wouldn't have happened if they didn't understand what the theoretical limits were. And I guess you can imagine the same thing will happen eventually for quantum communication.
Okay, thank you.
Any other questions?
I want to raise this question on when you say many things in the channel capacities and things like that, you have a E-bit and a bit, co-bit kind of a thing which is playing a role. But what do you would you like to comment on quantum discard playing any role in these things? Because in state merging and things like that, discard is said to have played a role. Is there any kind of, do you anticipate kind of quantification in terms of quantum discard? In
discord.
Yes.
I don't quite know the answer to that question. I haven't thought about that enough. Yeah.
Any other questions? In that case, I guess
have a
it's...
question.
Oh, I have a question?
I have a question.
Oh, you have a question. All right.
When do we eat?
Oh, I was just about to answer the question before you asked it. If the question is when, it's in 8 minutes. If it's where, I have no clue, but I'm sure that once we get out of here, it will be obvious. But so lunch is scheduled at 12:30, and we resume at 2 with the next tutorial. See you there. And let's thank Charlie and Umesh.
Lunch will not be on this campus. It is in the adjoining campus of the Institute of Hotel Management and Catering Technology. It's about 50 minutes walk from here. Sorry, 50 meters walk from here.